Welcome back. So today we are going to look at part 2 of transformations. In part 1, that was lesson 4, we looked at vertical stretch or a vertical compression or a vertical reflection. So that was a vertical stretch. When the entire function is multiplied by a factor of a, we get a vertical stretch, right? And we also looked at a vertical translation. So the entire function can move up or down, or you can have a horizontal translation where the entire function moves left or right. So all of that was the previous lesson or the last 2 lessons where we looked at several functions, including a few parent functions. And today we're going to look at what happens if the function is multiplied by if the x value is multiplied by a factor of b, okay? Now, how are these two different? In one case, in the vertical stretch, the entire function is getting multiplied by a factor of a, whereas in the second case, the x value is the one that's getting multiplied. Okay, so there's a big difference, right? And one ends up becoming a horizontal or a vertical stretch when you multiply the entire function by a, and the other one, when the x value gets multiplied by x, by a factor of b, it becomes a horizontal transformation, okay? So there are 2 separate transformations, and as soon as you see a function, you should be able to recognize, okay, is it a horizontal stretch or a vertical stretch? Now, just as in the previous case, where we looked at the a value or the absolute value of a, right? For those of you who joined the class a little late, when we say absolute value of a, we just mean the positive value, okay? So for instance, if I had, say, absolute value of -3 is just going to be +3, all right? And those of you who are not completely familiar with absolute value, you will also be wondering, well, what happens if it is absolute value of +3? It still remains positive, okay? The reason for that is because we just want to focus on the value and really not on the sign, okay? So if you want to talk about a vertical compression, or sorry, a horizontal compression, we're going to look at the b value, the absolute value. Well, is it a value between 0 and 1, or is it a value which is bigger than 1? Okay, so that's what we're looking at. Now, in the last couple of classes, I've told you that the horizontal transformations always go counterintuitive, right? And now we can see that here as well. If b is bigger than 1, say, for instance, if I had the absolute value of b is, say, 4 or 5 or 3 or whatever, any value that's bigger than 1, then you end up getting a compression and not a stretch, okay? As we go further along in the course, everything is called a stretch. We just have to recognize that one is a compression and the other is a stretch when we use the word factor, okay? Just by looking at the scale factor. But for now, we'll distinguish what's a compression and a stretch just to enable your understanding, all right? So if b is bigger than 1, then we end up getting a horizontal compression by a factor of 1 over the absolute value of b, right? And if b is between 0 and 1, we end up getting a horizontal stretch by a factor of 1 over b, okay? And if b is less than 0, we end up having a horizontal reflection or a y-axis reflection. So that's just the rules, just as in the previous lesson where I think in this lesson we also did the same thing, right? We had that was lesson 4, where we looked at what happens if the absolute value is bigger than 1, and what happens if the absolute value of a is between 0 and 1. I think there should be 0 and 1. Maybe I didn't fix that. Right? If that's between 0 and 1, and what happens if it is negative, right? Now, going back to our today's handout. Okay, so that is very similar to the ones that we looked at for the vertical stretch, okay? Except now we have to do 1 over b instead of just doing b, right? Right, let's, without much spending too much time looking at the definition, let's just go right into an example. So for the very first example, we have y is equal to f of 0.x. Okay, so here we have a function that is it's kind of like a discrete function, and we know it's discrete because there are dotted lines, but let's not get caught up in that. Here, the b value is 0.5. Okay, so that's the b value. Okay, it's because the x value is getting multiplied by 0.5. So b is equal to 0.5. Okay, and the absolute value of b is also going to be 0.5. Yeah. Now, what is 1 over b? Okay, so from there, we end up with 1 over absolute value of b is 1 over 0.5. And we know that 1 over 0.5 is 1 over half, which is nothing but 2. Okay. Again, for those of you weak in algebra, 1 over 1/2 is the same as 1 multiplied by 2 over 1, which is nothing but 2. Okay. So 1 over any number that's between 0 and 1 ends up becoming a number bigger than 1. Okay, so 1 over 0.5 is 2. So now what happens, this is a horizontal stretch, okay, by a factor of 2. What does that mean? That means every x value gets multiplied by a factor of 2, okay? So x value, so 2 multiplied by x comma y, all right? So all the x values get multiplied by a factor of 2. So that means if you have negative 6, 1, so we're looking at this value here, that value ends up becoming negative 12, comma 1. Okay, so this value ends up becoming negative 12, comma 1. Yeah, because the x values are doubling, right? Negative 4, comma 0 ends up becoming negative 8, comma 0. Okay, so all the x values change, right? What about this value here? Okay, this value here is going to remain exactly where it was because 0 multiplied by 2 is just 0, right? And here 2, comma negative 1 ends up becoming 4, comma negative 1. And 4, comma 3 ends up becoming 8, comma 3, all right? So it's going to go over there, all right? So, 8, comma 3, right? So these are the points. Okay, so if we want to join the graph, okay, and just make it and just see how it looks visually. Okay, we're going to connect all those points since the original graph is a dotted line. I'm going to stick with that and continue doing a dotted line. Okay, so here we go. And this is a horizontal stretch. As you can see, if I put this graph on an elastic sheet and pull the elastic sheet horizontally, this is what would have happened, okay? Just going to make this look less curved. Kind of looks like it's going through a curve. It's not, it's more a straight line, okay? There we go. So that is a horizontal stretch by a factor of 0.5. Now, let's move on to the next example. The b value here is 2, okay? The b value here is 2, okay? Or absolute value of b is also 2, right? So what happens with 1 over the absolute value of b is going to be 1 over 2, which is just 0.5. That means all the x values get multiplied by 0.5. 0.5 multiplied by x, comma 1, right? So all the x values end up becoming half of what they used to be. So negative 6, 1 now becomes negative 3, comma 1, all right? Negative 4, comma 0 ends up becoming negative 2, comma 0, all right? And 0, comma 4 remains exactly where it was, okay? 2, comma negative 1 ends up becoming 1, negative 1, and 4, 3 ends up becoming 2, 3, okay? So as you can see, even visually, it's very clear that the graph is horizontally compressed, okay? So if B is 2, we do not end up with a horizontal stretch. We end up with a horizontal compression, okay? So if B is 2, we end up with a horizontal compression, okay? So that is a horizontal compression by a factor of 1/2. Okay, so that is a horizontal compression. But what does this mean? It just means that horizontally the graph is just squished, and every time you have the B value, you have to do 1/, to get the factor. Some textbooks will use the word stretch, and they'll say it's a horizontal stretch by a factor of 0.5, which just means a compression, right? It's as you progress along, you don't use the word stretch for both stretch and compression, because it's kind of understood that when you say stretch by a factor of half, that means it is a compression, right? What about this? In this case, your B value is -2, okay? So if there is a negative, right, if there's a negative, what do we know? We know that that means there's a horizontal reflection, right? There is a horizontal reflection. And also, there is a stretch by 1 magnitude of B, which is 1 magnitude of -2, which is just going to be 1/2, right? So that means there is a horizontal compression, right? It's a horizontal compression by a factor of 0.5. That means all the x values get multiplied by 0.5. So in this particular case, there are a few cases where you have to pay attention to the order in which the transformations happen. But when it comes to stretches and reflections, you can interchange the operation. Okay, it's like saying, well, is it going to be different if I first multiply by negative and then multiplied by 2, or does it matter if I multiply by 2 and then multiplied by and then include a negative sign? It doesn't matter, right? If I had some number like 7, is it going to be different if I do 7 times 2, 14, and then insert a negative sign, or is it important to first insert the negative sign and then multiply it by 7? Okay, so that's pretty much why the order doesn't matter here. Okay, so you can do it in any order. I'm just going to compress it first, just for you to see what happens. So -6, 1. Actually, we already did this, so I'm going to start with that. That's going to be -3, 1. Okay, then we go with this. -4, 0 is 2, 0. And then 0, 4 is going to be just 0, 4. And 2, -1 is going to be 1, -1. And 4, 3 is going to be 2, 3. Okay, so that is, that's what happens with the function. So there we go. This is the function without the horizontal reflection. Okay, it's just the function as is, with just only the horizontal compression. Okay. So the light blue graph is just going to be f of -x. All right. That's just, sorry, my mistake. The light blue is just going to be f of 2x. Okay. But we need f of -2x, so you're just going to reflect it. Okay, so this point, right, which is -3, 1, is going to go over here. Is going to go horizontally reflect over there, right? So that's where that's going to go. Okay. So this point goes over here. Okay, so basically what I'm trying to say is that -3, 1 ends up becoming the new point, okay, which is just going to be 3, 1. Okay, so this is a horizontal reflection. okay? Only the X values flip sign, okay? And then negative 2, 0 becomes 2, 0, right? 0, 4 stays where it is. 2, negative 1 becomes negative 2, 1. And then 2, 3 becomes negative 2. Sorry, I think I made a mistake. You bear with me a second. Let's try this again. We are doing the light blue dotted one. So negative 3, and then this point is over here, and that point is invariant. And then a negative 1 becomes negative 1, negative 1, and then this point 2, 3 becomes 2, negative 2, 3. Okay. So this is your final graph. Okay, so this is what we're looking for, right? This is your final graph. What is this graph? This orange graph, okay, is f of negative 2 of x. Okay, so you can go stage by stage. I would rather you go stage by stage, especially when there are multiple transformations. At least do 1 or 2 transformations at one go, and don't try and do more than 2 transformations at any given time. Okay, just to avoid careless errors. Right, let's move on to this one. Now, what's up with this graph? There is no function given. You have to identify the parent function, okay? And based on lesson number 3, we looked at 5 different parent functions. And in this case, the parent is going to be y is equal to square root of x, or f of x is equal to root x. So that's what we're going to graph. 0, 0, 1, 1. We looked at some key points in this graph. So this is your parent function, which is nothing but y is equal to root of x, or if you like to call it, you can call it x, f of x, right? Now, what are the transformations on this? There's a 2 multiplying that, okay? That's a horizontal compression. Now here order becomes important, right? So if you were evaluating this, you'd first multiply the x by 2, and then only after that you would do the negative 1, right? You would then subtract 1 out of it. So if you're evaluating that function for, say, a given value of x, you'd first multiply it by 2, and then you would subtract that value, you subtract 1 from that value. So we follow the order of operations. So you say horizontal. So that's the b value, b equals 2, okay? Okay, so that means horizontal compression by 1 over 2, okay, or 0.5. Okay, so that means you end up having all the xy values from the parent function, right? All the xy's from the parent function ends up becoming 0.5 comma 0.5x comma y. Okay, so that is that's one of the transformations. The second transformation, there's more than one transformation going on here. The second one is a vertical translation, because the second operation is not happening on the x. Okay, if I had something like this, it would not be vertical. But if I had something like this, that is vertical. Okay, you have to recognize the difference between the operation happening on the x and the operation happening on the entire function, on the entire parent function, right? In this case, it's happening on the x value, it's happening outside the x value. So it is a vertical transformation. So vertical translation, and because it's -1, it goes down, okay? Vertical translation, down 1 unit. Okay, so let's try to do the horizontal compression first, right? So what happens here? So you have 0, 0 is going to stay exactly where it is. That's going to stay there. 1, 1 is going to end up becoming 1/2 1. Okay, so that becomes 1/2 1. 4, 2 becomes 2, 2. And 9, 3 becomes 4.5, 3, right? So these are the points, okay? I'm going to add one more point, okay? Even though I've given you only 4 points on the parent graph, I'm going to end up introducing another point because the next point after this, after 9, 3, right? What is the next point after 9, 3? It should have been 16, x is 16, y value is 4. So instead of 16, 4, now I'll have 8, 4, okay? Don't worry too much about where did Miss A get this value from? Okay, that's just 16, 4 has become 8, 4 now, okay? Let's try and keep up with it. If not, don't get bogged down by that little detail, okay? So here is, what is this function? This function is y is equal to root of 2x, okay? So this is only if it was 2x. Now we have to do this whole function and we need to bring it down by 1 unit. So that goes down there. This comes down 1 unit. This comes down 1 unit. Okay, that comes here and this comes here. Okay, so this is your new function. Okay. So this is your final graph. Okay. I hope that's somewhat clear. Let's try the next one. Well, what's b here? That's a b value. So the b value is -1. So it's going to be no horizontal stretch or compression. Okay. Why? Because the absolute value of b is, sorry, this pen is refusing to write. I'm trying this. Oh, there we go. Just this means no horizontal stretch or compression. You don't have to write that on a test. It's just, I'm writing this here to add clarity. And then you can say there is, however, a horizontal reflection, right? Also, we have something else going on, right? The d value is 3. So d equals 3. What does that mean? This means it is a vertical translation up 3 units. Okay. I hope that's clear. Now, again, in order of operations, just to keep things simple, just do all stretches and compressions before you do translations, okay? There's also other small things you need to pay attention to, like factoring out the b value and all that, but we can add those layers as we go along, okay? For now, just know that you're going to first reflect and then translate, okay? So let's reflect and then translate. Okay, first of all, what's the parent function? The parent, as we would have identified, is f of x is equal to root x, or you can just call it y is equal to root x. I don't care how you label the parent function, as long as you have it sketched out correctly, right? So this is your parent function. So this is y is equal to root x, or f of x is equal to root x. There's your parent function. Now you want to reflect, okay? So you want to reflect this. So just go in the opposite direction, just mirror image it. So 4, 2, right? -4, 2, 9, and 3. I haven't left myself much space there. I'm just not going to worry too much about that for now. If I had more space, I would have I should have given myself a little more space there, but for some reason I haven't. Okay, so it's kind of going to go like that. Okay, we have 3 points. It's not too bad, okay? Now, this graph is nothing but y is equal to negative root of x. Okay, one is the root of x graph, the other is negative root of x, right? So that's what this graph is. It's just nothing but negative root of x. Now we're going to move the whole graph up by 3 units. Okay, so 0, 0 moves up 1, 2, 3. And just count the grids and keep sliding it up, right? And that is your graph. That's your final graph. So that is g of x is equal to negative of, root of negative x and then plus 3. Okay, so this is your final graph. Okay, so that's the graph. I color coded it. Yeah, so just follow the color coding and the labels. All right, let's do one more or a couple more. All right, here the b value is factored out. Okay, factor out b. Okay, so what is the b value? The b value is -1. Okay, again, there is no stretch or compression, there's only a horizontal reflection. Okay, so that's going to give me, right? So that's going to give me a horizontal reflection. What else is going on? Now, if I had absolute value of x minus 2, I would call it a horizontal translation. If I had absolute value of x minus 2, I'd call it a vertical translation. Now that these two are completely different. Okay, so this is horizontal translation, right? And this is a vertical translation, right? The operation is happening not on the entire function, but just on the x value, right? So we are going to look at the parent graph and say, yeah, that's happening on the x value. Okay, why? How do you know that? You have to look at the parent function. The parent function is y is equal to absolute value of x, right? Is the operation happening outside the absolute value or on the x? It's happening on the x. So on top of the first transformation, okay, the horizontal reflection, we also have a vertical, so basically a horizontal reflection. We also have horizontal translation to the right, okay? So basically translate right 2 units. Okay, so we're going to just move this over, right? All right, before we do anything, we need to sketch the parent graph. So this is the parent graph, absolute value function 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and so on and so forth. Okay, because the absolute value is nothing but the negative, only the positive value. Okay. Okay, so that is y is equal to absolute value of x. That's your parent graph. We're going to reflect it horizontally. Well, what happens if you reflect it horizontally? Take a guess. If you put a mirror on the y-axis, what happens? It's just going to go right there. Okay, so that is y is equal to negative of x. It's going to look identical. So y is equal to x and y is equal to negative x look exactly identical. Okay, so that is y is equal to negative x. Okay, so that's both those graphs, the green graph coincides with the blue graph. Okay, right. Now there's one more it moves right 2 units, so your final graph is going to look like this. Okay, it just moves right 2 units. So just take the whole graph and just move it, and you're done. Okay, so that's that. So here's your final graph. Okay, so I'm going to label it over here. So this is g of x is absolute value of negative of x minus 2, and then that. Okay, so that is your final graph. Okay. This graph is nothing but a parabola. Okay, so your parent graph. Okay, so that's your parent graph. Yeah. Now, there are two transformations going on here. There is a horizontal translation to the left or to the right. It's x minus negative 3 square minus 2. Okay, so C value is negative, so it's going to move left. Okay, horizontal translation left. Okay, how many units? It moves it horizontal translation left 3 units. I'm running a little tight on space there, so I'll just write it here. 3 units. Okay, so essentially what we're doing is we're taking that g of x and then writing it as x minus negative 3, all of that square minus 2. Okay, so that plus can be written with double negative. And why are we doing that? Because there's an inbuilt minus sign in the horizontal translation. Okay, so if you go to the lesson 1 notes, okay, you see that there is an inbuilt negative sign here. Okay, so that's the reason we do that. Okay, try to bring it back to the form. Okay, so now there is also second translation going on, and it's a vertical translation or vertical shift, if you want to call it, down 2 units. Okay, so if I wanted to do it stage by stage, at this point you probably want to do it in one go, and that's perfectly understandable. But since some of you are probably still wrapping your heads around this, I'm going to do it in 2 stages. So I'm going to move left 3 units. Okay, and then okay, so this is the graph that just moved left 2 units. Okay, so this is y equals x plus 3 the whole square. Okay, so that is halfway into the transformation. The final graph is going to look like this. I'm going to move everything down by 2 units. So bring that down 2, down 2, down 2, and you're good to go. Okay, so this is what we mean by graphing using transformations. All right, so that's your final graph. This is g of x equals x plus 3 the whole square minus 2. Okay, so that's that graph. All right, I think by now you're probably getting a little tired. You can pause the video, get up and stretch a little, and then come back and watch the video. All right, I think by now you might be getting a little tired, right? So feel free to just pause the video and get up and stretch. Our next function is f of x is 1 over x minus 3 plus 2. Again, we have to look for the parent because there's no graph given. So the parent function is y equals 1 over x. Okay, going to draw the parent function 1, 1. Okay, you can add these points if you want to, just to make your graphing a little smoother. Okay, just going to stay with 1, 1, and then use the other two as guiding points for graphing, not so much for really focusing too much on it. Okay. So I have this part of the graph going like this. Okay, so this is the parent graph. There is a horizontal and vertical asymptote as well in the parent graph. Okay, so there is a vertical asymptote. The y-axis is also called the x is equal to 0 line. The x-axis is called y is equal to 0 line. So that's the horizontal asymptote. That's 1, 1. And this is -1, -1. Okay. There we go. All we've done is just draw the parent graph. Okay. We have to identify the transformations. So from here, we're looking for the transformations. What are the transformations? One operation is happening on the x, the other is happening on the 1 over x parent graph. So you're going to say, in this case, the order doesn't matter. You can either move up to and then move sideways, or you can go sideways and then move it up. The order doesn't matter here, okay? So I'm going to say vertical translation up 2 units. And after you do that, you're going to horizontally translate to the left or to the right. It would be to the right. 3 units. Okay. So let's do it stage by stage. If you're really comfortable doing it all at one go, go ahead, but I prefer doing it stage by stage. When you go up 2 units, oops, sorry, there we go. When you go up 2 units, okay, your horizontal asymptote is also going to move, okay? You're going to go up 2 units, you're going to take your horizontal asymptote with you, okay? So that's your new horizontal asymptote. Actually, I'm not going to do it stage by stage. I lied. I'm going to do it all at one go. Okay, it makes it so much easier. Otherwise, you're going to have too many graphs running amok here because each graph has 2 separate arms. Okay, so I'm going to do everything at one go. I'm just going to move up by 2. That means your horizontal asymptote also moves up by 2. Okay, so the vertical transformation takes your horizontal asymptote with. Takes it up 2 units. Okay. And then it translates right 3 units. So the vertical asymptote as well moves along with it. Okay, so that's your vertical asymptote at x is equal to 3, right? So this particular point here, right, this particular point here, 1, 1, goes up 2 and right 3, okay? So it goes up 2, okay, and then right 3. So that's where it goes and ends up. Okay. I'm going to remove the dotted lines there so that for clarity you see so you take it up 2 and right 3. Okay, so that's what I'm doing. Okay. So I'm just going to go up 2, 3. Okay. Same thing here. Up 2, 1, 2, 3. Okay, so that is where your new graph is. For the time being, I'm going to remove that so that it's not too cluttered. Okay, and just write this as 1, 1 here. Okay. So what does the graph look like? It approaches the vertical asymptote and then approaches the horizontal asymptote. Same thing here. So that's your final graph. Okay. Now, this part B to this question, the domain and range. The domain of f is such that is defined for x such that x is not equal to, what value does x never take? It never takes 3. Okay. The range of f is such that y value is never, where does the y value not exist? I mean, as you're going up and down, it doesn't exist at y equals 2. Other than that, it exists everywhere else. Okay. So with that, I complete today's lesson. I understand it is a long lesson. I hope this was somewhat clear. And I will see you back in class on Friday, and try your homework, and please help each other out. All right. Thank you. Bye-bye.